money, and it'll beep, but it's not in our control. Oh, there we go. Temporary. Hold up. Sorry. I will give you this microphone if you have any jokes or.
Really good introduction. I can just start with an introduction. Slides are getting fixed. Is that a change? Okay.
Yeah, there will be no words to say.
I think you might be trying to find slides on my laptop.
Oh. Yeah. Can you do it PowerPoint mode? Yeah, thanks.
Close your eyes, Ted. Close your eyes.
We're going to market.
With how good you are at getting data, I'm surprised I didn't find slides.
That's not even fine.
Yeah, thanks. Good morning, everyone. Thanks a lot for inviting me to give this presentation. My name is Maulik. I'm the Director of Clinical Informatics at Optum Health. Today, I'm going to talk about knowledge engineering and clinical decision support, the benefits, the challenges, and opportunities in the space. So I'll start with why do we need knowledge engineering and clinical decision support? So clinical decision support, or CDS, aims to provide timely information using updated biomedical knowledge and context-sensitive information. It helps in decision-making for providers about a patient or a cohort of patients. Generally, CDS is deployed at the point of care within EHR systems, or it's used within clinical quality analysis and reviews using population data. And theoretically, if done right, there are studies about this. CDS can potentially lower cost, improve efficiency, improve patient outcomes, and reduce inconvenience for both patients and providers. Some of the examples of CDS applications are computerized alerts and reminders, clinical calculators, clinical clinical calculators, diagnostic and therapeutic support, condition-specific order sets to order lab tests or medications, focused patient summaries, and care gap analysis that is done for using population data. So the challenges are, and this community is familiar with these challenges, there is an explosion of biomedical knowledge and data. Krishna gave an amazing talk, Hans gave an amazing talk. I won't beat the horse, but there's a lot of knowledge that is published as unstructured and structured sources. You have clinical trials, scientific publications, guidelines, drug databases, pathway databases. Simultaneously, there is an explosion of data. There is a lot of biological data, patient data, sensor data, other forms of data like social economic determinants of health. And a lot of time, the providers need to analyze all these different sources of patient data in the context of what is available, in the context of all the available biomedical knowledge to make a decision at the point of care. So this becomes challenging. And so some of the challenges are familiar with the knowledge graph community. CDS applications need accurate, complete, updated, trustworthy, and actionable knowledge. So these are the three metrics that have been mentioned several times since 2018, I think, when it was first presented, that the challenges are around completeness of knowledge, freshness of knowledge, correctness of knowledge. And within the biomedical domain, especially within CDS applications, these challenges become much more complex because there's a lot of data, there's a lot of different knowledge. It needs to be trusted and accurate within CDS applications, and this knowledge can arise from several sources. A knowledge graph is a great solution maybe for tackling some of these challenges. I won't define a knowledge graph. A lot of people have already done that. And this is my idea of a knowledge graph where you have different nodes and edges that represent the biomedical entities and relations of interest. You can have provenance information. You can have certain ontological characteristics in the graph. And then you can link all the different patient data to different clinical concepts and the biomedical concepts in the graph. And then theoretically, you could bring in data and knowledge from other sources. So you can bring in, as I mentioned, the social economic determinants of health, drug-drug interactions, drug gene protein targets, things like that. And your graph will exponentially become huge, and it obviously will change over time. So you need to have scalable solutions on that. Now, knowledge graphs might seem a silver bullet, but like there are a lot of different challenges, and especially in the clinical decision support applications, there are more crucial challenges. So I'll talk a bit more on that. But before I delve deeper into the challenges, I'd like to present the slide. Biomedical AI has been here before. A lot of people are familiar with like knowledge engineering. Back in the 1970s, there were a lot of different investment cycles on semantic networks and use of knowledge-based systems, expert systems. There are some nice references that are linked here in the slides from really old papers back in 1970s. And some of the ideas involved back in the day, and these are actual ideas that were present in the paper about domain-specific knowledge, implicit and flexible knowledge, encoding of knowledge, multiple sources, networks, interoperability, explanation of reasoning. These are ideas that I actually, for this slide, I have taken it from these papers that are referenced here. So these ideas have been there from back in the 70s. And some of the challenges that were mentioned is that it's very difficult to express all the different rules formally and interpret a domain expert's mental model. In the case of CDS applications, it's the clinician's mental model. And it's difficult to scale and adopt all the different standards. And I just view like knowledge graphs are just like the tip of this trajectory. Like you see the Google knowledge graph from 2012. It's only 10 years. It's been 10, 12 years, but like you can go all the way down to Internet to Mycian, to Maxame. So there's a lot of history in knowledge engineering. So what are the challenges then? And so some of these challenges are still prominent, and Krishna gave a great introduction, so I won't go that much into deeper here, but there are a lot of different code systems. There are a lot of different terminologies in biomedicine. They often use different entity notations with minimal reuse and interlinking. And when we talk about CDS applications at the point of care in EHR systems or over population data, you need to have linking, querying and reasoning abilities across all these different code systems because they might be used for different data sources like sources around variables, monitoring, biobanks, drug databases, etc. But now I'll talk about something more complex in clinical decision support. So the first idea is about value sets. Value sets are a group of clinical concepts created from different code systems and terminologies. Theoretically, all members of the value set are considered to be equivalent. And this is a picture of a screenshot of the National Library of Medicine Value Set Authority Center. A lot of different organizations create these value sets on this application. Theoretically, these represent all the different ICD-10 codes or SNOMED-CT codes or LOIN codes or CPT codes that represent a particular clinical concept. So it can be a concept on hypertension. It can be a concept of diabetes conditions. It can be a concept on clinical systolic blood pressure. All of these can be combined to build these value sets, which are a group of clinical concepts. Now you start building up on these blocks. So now we talked about value sets. Now we talked about clinical rules. How do we identify if a patient has hypertension? You can use the patient problem list, look up their active diagnosis, and see if their a problem list has any of the ICD-10 codes or the SNOMED-CT codes that represent hypertension. Or you could look at their lab observation values, their systolic blood pressure, and then you can infer whether that value of the systolic blood pressure observations are greater than 150 millimeter of mercury. There are two separate events, and like look back for like a last year, like so two separate events in the last year. Both of these definitions are correct for hypertension. How do we represent this in graph? Maybe it's not possible in graph. Maybe graph is not a solution. We start. Oops, sorry. we start building up on the simple clinical rule. So what I mentioned was a simple clinical rule. Now we start building up on that. Combine multiple clinical rules, multiple value sets, multiple individual codes to build this complex clinical calculators or questionnaires. So here you have the ASCVD risk calculator, which is a very popular clinical calculator that is published by the American College of Cardiology to determine if a patient has ASCVD risk or not. It uses different concepts from systolic blood pressure, diastolic blood pressure, cholesterol, LDL cholesterol, things like that. And each of this could be represented in different ways in the EHR system using different ICD-10 codes. Another example is a PHQ-9 questionnaire for depression assessment. Same, like different line codes are used, and like the clinician or the provider will combine all the different questionnaires and compute whether the patient has severe questionnaire items and compute whether the patient has severe depression or not. There are a lot of these different clinical calculators. This is knowledge. This is clinical knowledge. And there is MD Calc, which has a lot of different examples here. Now we are building up. We are building up for clinical decision support. We are combining clinical calculators, rules, questionnaires, value sets, everything to create this complex decision trees and flow charts. And then the leaves of the decision tree can indicate some action, some recommendation, some complex search sets, user segment, ordering a lab test or a medication, things like that. We're combining all the different building blocks to build this decision tree. And I'm not done yet. We are combining all the different decision trees to create all the huge guidelines. So ADA, ACC, AHA, American Diabetes Association, American College of Cardiology, American Heart Association, all of these publish all those guidelines, which are updated every year. And they're composed of multiple decision trees, flow charts, recommendation tables, referrals. All of this knowledge exists in a clinician's mental model. How do we create CDS applications that combines all the different knowledge so that it can help the clinicians? Knowledge graphs are not the only solution here. And like, maybe you need to combine a rules engine. Maybe you need to bring something else. Maybe, I don't know, generative AI. It's up on the hype curve. Generative AI is great. As just one slide of language models that I wanted to put here, but it's like difficult to use generative AI and language models within clinical decision support. Some of these challenges have been mentioned several times in Knowledge Graph Conference. One key challenge that I think is very crucial is auditing and explaining what is the underlying reasoning, why you are making a recommendation, why you are using CDS to generate a certain risk score or something. That needs to be explainable by the LLM model, which is difficult. And then finally, we have the FHIR specification, like, so everything on FHIR. That's my term that I use because there are a lot of different things that folks are building on top of the FHIR meta model for like information exchange. So there's like the CPG on FHIR, which is the clinical practice guideline of FHIR, evidence-based measure on FHIR, CDS hooks, etc. So how do we, and these are standards are useful for developing CDS applications that can be used at the point of care. So how do we combine these standards, the knowledge graphs, language models to drive CDS applications? So I know I'm short at time, so I'll like wrap up a bit quickly here. But I've talked about this knowledge graph ecosystem a while. So knowledge graph, the graph is just one aspect of it. You can have several different components that can leverage the graph or go into the graph to help your clinical decision support applications, which is the end stage here, which can use some patient data. And there are different avenues where you could combine the knowledge graph with the standards, with language models. So you've got your language models, you've got your FHIR meta model, and then all of these combined can drive the CDS application. So some of the avenues where you can think about combining all this is, for example, concept mapping. FHIR has a concept map meta model for representing linkages between different terminologies. Value sets, I talked about value sets. FHIR also has a value set a profile for representing groups of clinical concepts, and knowledge graphs and language models can help to create those value sets. Rules, there are different FHIR resources and clinical reasoning resources, which are as part of the CPG on FHIR implementation guide. knowledge graphs and language models can be used to create the CPG or file implementation that can drive the clinical reasoning. So there are avenues where we can think about as a community how the graph can help, and language models as well. And then finally, care gaps analysis. So once again, knowledge graphs and language models can help provide the knowledge for driving these different standards. DQM stands for the data exchange for quality measures. So there is another implementation guide that FIRE community, the HL7 community has created. So we could combine these two to drive the reasoning through this particular implementation guide. So there are avenues, and I just wanted to wrap up with saying that knowledge graph is not a silver bullet, language models is not a silver bullet, but all of these things combined together maybe can drive towards better clinical decision support in the 21st century. And obviously it needs a lot of different stakeholders to do that. And that's the end of my talk. And thanks a lot again.
Maulik.